Before people settle with technology, let me speak in general. I knew that several students were attending this particular conference, so I thought it would be better to touch upon some simple applications of Maclaurin series, which we have recently used in solving very complex problems. So what is important is, especially when you are undergoing a course in mathematics, whether it is undergraduate or postgraduate, you must understand that there are various connections. Now when we were doing our MSc, little did we know that there is connection between topology and differential equations. Okay, little did we know that there is connection between differential geometry and fluid mechanics. So like that, each topic that we study, there will be some connection or the other, and those connections, if we see, we will be able to solve many different types of problems. Maclaurin series is one which can be used in many contexts. The concept is very, very simple, but it may be used in lot of problems. So now we note that Maclaurin series can be used to solve initial value problems. We all know this. Okay, so you have the Maclaurin series. The Maclaurin series involves derivatives at 0. So if we are given initial conditions, so the differential equation can be solved as a Taylor series solution or a Maclaurin series solution. Now suppose instead of an initial value problem, I am given a boundary value problem. Okay, and I insist that I want to use the Maclaurin series. So what is it that can be done? When I want to use the Maclaurin series, I know that the condition must be specified at 0. But now you have a boundary value problem. So the boundary value problem means what? Not all conditions are at 0. You would have certain conditions at say 1. So what we will do is, we do not know all the initial values. So in place of the right hand boundary conditions at 1, we simply replace the unknown initial conditions and then solve as though you know them. And then those conditions, those initial conditions which you do not know, ultimately they'll have to be determined. So how do you determine that? Now what have you done? The right hand boundary conditions you have replaced by initial conditions which were not known. So now you go back to the right hand boundary conditions and determine those unknown initial conditions which you have. So you see here that Maclaurin series can after all be used in solving boundary conditions also. Okay, yes. So, that previous one was okay, I think. No, this I'll have to move. You make it one full page. What is it? Control L F5 or? Ah. This is working, but I want the full page. Yeah, that should be fine. So we'll take up some very simple things, okay, things which all of us will understand. So we'll start with, for example, we'll start with this equation. For example, what is the 2-point boundary value problem? 2-point boundary value problem will involve the conditions at 2 points. Okay? And if it's an initial value problem, what does it involve? It involves condition at 1 point. So that is what we have written. Now, in addition to these two, you also have what is called as a boundary eigenvalue problem. Now, what is the difference? Now, in these cases, that is the boundary value problem and the initial value problem, this omega squared, which I have written out there, that is fixed. I need not determine that. In the case of a boundary eigenvalue problem, the lambda squared, which I have written there, that is also to be determined. Because the solution or the eigenfunction exists only for a specific value or a number of values of lambda, and that lambda is known as an eigenvalue. Okay, so lambda is also an unknown. So if I solve this, suppose I am given this boundary condition. Okay, so I can solve this. So you see here, in the course of my solving the differential equation, I get the value of lambda to be plus or minus n pi. So what is that? What does that mean? For those specific values of lambda, which I am calling as lambda n, the solution exists. So that lambda, those lambda n's, I term it as an eigenvalue. Only for those values the solution exists. Okay, so we all know this. So now I write down the solution. My given equation is linear. So any solution of the equation that I have, I can superpose those solutions. So that's called as the principle of superposition. So I am making use of them. Now in the case of an initial value problem, what I'll do is, I told you this lambda squared, in the case of an initial value problem, it is not to be determined because that is not an eigenvalue. Lambda squared is fixed. So when lambda squared is fixed, all that I'll have to find out is my y of x. So I'll determine that using the Taylor series like this. So you have the differential equation here. So I know y of x naught, y dash of x naught. Then the remaining, that is y double dash of x naught, I can determine from the differential equation. So I can now obtain the solution in the form of a Taylor series. When x naught equal to 0, it is a Maclaurin series. Now, such a solution can be obtained for both linear as well as non-linear differential equations. Okay, so this is what you have. Now, for the purpose of understanding, I am considering an ODE. You can do a similar thing in the case of PDE as well. Okay, so this is what you have. Now what does this tell you? This tells you that when I want to find out the solution of a given initial value problem, I can obtain it in the form of a power series. Okay, what is the reason for that? Why would I think of finding out a power series solution? I know that many functions which are nice, they have a Taylor series expansion, and that is a consequence of which theorem? You would have all done that in analysis, the Stone-Weierstrass theorem. Okay, so we know this, so that is the reason why we attempt the Taylor series solution. Now we can obtain the power series solution using a very structured way. The Chinese came up with this method, and this is called as the differential transform method. You see the brilliant way in which the Chinese recognized that the Maclaurin series can, for example, be viewed as a transform. Let us see this. So I write down my Maclaurin series. I write down my Maclaurin series in this way. So now this is evaluated at x equal to 0. So it is independent of x. So it becomes a function of only n. So that I'll suggestively write as capital Y of n. So now you see here that y of n is, from y of n I can obtain y of x. But what have I obtained here? From y of x I have obtained y of n. Okay. So you see here, from y of x I obtain y of n. So you can think of this to be a transform, a differential transform. Okay. So from y of n I can again get back my y of x. So this is an inverse differential transform. So I can find out the inverse differential transform of the first order derivative, second order derivative. So I can solve this. So I don't want I'm leaving these slides on the system. If any one of you are interested, you can just go through that. Okay. So I don't want to spend much time, but you can just be convinced that obtaining the solution as a Taylor series, you can make use of the computer system, okay, and very easily obtain the power series solution. So I'll not spend time on this, but I'll spend time on the boundary value problem. Okay. So I'll take d squared y by dx squared plus 4y. As I mentioned earlier, in the case of initial and boundary value problems, the lambda squared, for example, that is 4 here. So that is fixed. I need not find out. Okay, so this is a boundary value problem. I have conditions specified at 2.0 and 1. So in place of this yn equal to 0, which is the right hand boundary condition, what am I doing? I am considering y dash of 0 equal to alpha. In place of y of 1 equal to 0, I am considering y dash of 0 equal to alpha. But my alpha is as yet unknown. I have to determine alpha. But I'll just go ahead as though I know alpha. Okay, so what do I do now? I find out the solution of the equivalent initial value problem. So my solution y of x will now be determined in terms of alpha. Now, but I should ultimately know what alpha is, and how do I do that? I now go back to my right hand boundary condition. So whatever yx I have obtained, I use the condition y of 1 equal to 0, the right hand boundary condition. That will give me the value of alpha. So that is what I have done here. Alpha, I will obtain it to be 15 by 7. So you see here that Maclaurin series can be used to solve initial value problems that we knew. Maclaurin series can be used to solve boundary value problems. Okay. But the most amazing thing is Maclaurin series can be used to solve boundary eigenvalue problems. That is something which is new. Okay. I think the tea is more interesting. So, I think I'll stop my talk and have some tea, I think. So we'll come to boundary eigenvalue problems. So what did we say? In addition to the solution, that is the eigenfunction, I need to determine the eigenvalue as well. Only for those values of the eigenvalue will I have a solution. Okay? I just don't know why talks are arranged. So let us see this. So here I'll take the problem. So it is a boundary value problem. So conditions are specified at 2 points and lambda is also to be determined. So it's a boundary eigenvalue problem. So what we'll do is, now since lambda is also to be determined, I will consider a trick that we played with shooting techniques. So when we wanted to find out the eigenvalue in the case of a boundary eigenvalue problem, while using the shooting technique, we introduced an artificial differential equation. So that artificial differential equation is this dE by dx equal to 0. I am just calling lambda squared as E. So I have d squared y by dx squared minus Ey equal equal to minus Ey. So I take dy by dx equal to z, dz by dx will now be minus Ey, and y of 0 equal to 0. What did I do with the boundary value problem? Instead of the right hand boundary condition, I will now consider an initial value which I do not know, and alpha is to be determined. So, and what is the nature of the eigenvalue? You see, I took up a problem and wrote down there that lambda is plus or minus n pi. Does it depend on x? It does not. So what I am writing here is essentially that itself. I am just saying that E does not depend on x. So that is the artificial differential equation which I am using. Now because I have an additional differential equation, I have an augmented system, I need an initial condition for that as well. So E of 0 equal to E naught. So now alpha is an unknown, E naught is also an unknown. Okay? Alpha is an unknown, E naught is also an unknown. I just solve this differential equation in the usual way as I normally do. Okay, I just solve this differential equation in the normal way. Meaning, I make use of Maclaurin series expansion. So, let me say this. So, here I have this system of 3 equations, but I don't know alpha, I don't know E naught, so I have 2 unknowns. But to find out these, how many conditions do I have? I have just one condition, that is the right hand boundary condition. That is y of 1 equal to 0. Meaning, I have one condition and 2 unknowns, and that forms an inconsistent system. I'll have to close the equations, meaning I'll have to have as many unknowns as the number of conditions. So what I do is, I simply normalize the equations. What is the focus in this problem? The focus in this problem is on the eigenvalue. I am more interested in the eigenvalue than the eigenfunction. So what I'll do is, I'll just scale the the variables y and z, I'll just scale by alpha. So what happens to this system now? What happens to this system? Okay, that system becomes this. So z of 0 equal to alpha will now be z tilde of 0 equal to 1 because I am dividing by 1. I mean dividing by alpha. So now I get a system in which I have one unknown and one condition. Okay, so the given system is now consistent. So I am able to determine everything. Remember, I am able to do this because in this problem, the emphasis is more on the eigenvalue and not on the eigenfunction. That is the reason why I am able to do this. What you call as normalization in shooting method, it's exactly that which I am using here. Okay, but I'm using it in a very simpler way, that is making use of the Maclaurin series. So I have a normalized initial value problem, so I'll solve it. I mean, I can solve that initial value problem by Maclaurin series.
Sir, for your remarkable presentation, it's truly enlightening. Now I request Professor R. Rangarajan sir to present a memento as a token of respect. Next invited talk is by Professor S.K. Narsimurthy. I request Professor Rangarajan sir to introduce the S.K. Narsimurthy sir.
I excuse the audience. I also want to use little bit of Kannada. So, Professor S.K. Narsimurthy is a Gandugali from Kote Nadu. He is from Chitradurga. It is my fortunate that both of us started the journey of this academics in 1996 from Kuvempu University. And he is going in a very high speed. So I am still in a very low speed. He is already senior professor and senior most in the campus. And he is the finance officer of the Kuvempu University. So let us, yeah, thank you. Thank you. So he has started a very humble beginning from a family of a farmer, and he is a rank student throughout his career. So he did his BSc from SJM College, Chitradurga, and he did his MSc from Kuvempu University, MPhil from Kuvempu University, also PhD in differential geometry from Kuvempu University. He has vast administrative as well as academic experience. So he is member of PMEB Director, Academic Council, Finance Officer, Director of Collegiate Development, Director of School of Physical Sciences, and Director of Dr. B.R. Ambedkar Study Center. So he has many significant contributions. His research area is differential geometry of manifolds, differential geometry of insular spaces, general theory of relativity and cosmology. And he has more than 176 publications. He is reviewer of many journals, and he has guided more than 25 PhDs successfully, 2 postdoctoral studies, and he has many professional memberships to his credit, and he has visited many countries, and he has published 5 books, and I would very glad to read his awards, honors and recognitions. So late Dwarkanath Memorial Award for the best paper and best presentation by Tensor Society of India in 2009, Associate Fellow Award, Indian Academy of Physical Sciences, Allahabad 2021. Chairman, Textbook Review Committee from 1st to 7th Standard, Textbook Society, Government of Karnataka. Chairman, Textbook Review 1 to 7th Standard, Government of Karnataka. Vice President of Tensor Society of India. Secretary and Coordinator of Indian Academy of Physical Sciences, Allahabad, the editor of Tensor Journal, Tensor Society of India. Thank you, sir. So I invite you to deliver your invited talk.
Thank you very much, sir, for your nice introduction. Good afternoon. Because we are already from morning, we are enjoying the different talks, right? Respected chairman of this session, my dear senior professors, especially my brother, Professor R. Rangarajan sir, we are sharing our foods for 3 years in the beginning in the same room. Is very much well-wisher for me, and another well-wisher for me for Professor Siddeshwar sir. It is very honor for giving this talk in front of all my senior colleagues also, madam, and my Dharwad University colleagues, Shirahal Shetty and Ramane sir. Mangalore University, the Chandru is also coming. This is the second talk in this hall. Dear friends, one thing, this is just enjoy 3D picture, okay? Because it is not applied mathematics, it is the applications of mathematics, okay? Because I am a researcher in pure mathematics, not applied mathematics. My area of research is differential geometry, but it is difficult in differential geometry. That is why very recently we have to switch over and identify some applications. Of course, this is what I am thinking is very much suitable for this conference, advances in mathematics. That is why I will collect only for a preliminary ideas, very basic ideas, because I know when we can enter into the deeper and deeper of our pure research, it is difficult to sit even, not listen, right? ಕೂತ್ಕೊಳ್ಳಿಕ್ಕೆ ಆಗಲ್ಲ, ಇನ್ನು ಕೇಳಲಿಕ್ಕೆ ಎಲ್ಲಿ ಸಾಧ್ಯ ಆಗುತ್ತೆ ಅಲ್ವಾ? ಹಾಗಾಗಿ ಜಸ್ಟ್ ಐ ವಿಲ್ ಎಂಜಾಯ್, ಐ ಥಿಂಕ್ ಯು ಕ್ಯಾನ್ ಎಂಜಾಯ್ ದಿಸ್ ಸ್ಲೈಡ್ಸ್. ಮೈ ಟಾಕ್ ಈಸ್ differential geometry applications to relativity and cosmology. Look at that, very interesting fact it is. Of course, everything is pure science. Mathematics, differential geometry, the theory of relativity, and the evolution of this universe, that is cosmology, isn't it? So entirely that is different concept. I hope that I can carry all of you to the unknown world. So that is very basic idea I am introducing here. The relativity and cosmology, I think dear friends, you can imagine that how this differential geometry means branches of mathematics are originated or introduced in the classification of the world of mathematics. ಹೊಸ ಸಬ್ಜೆಕ್ಟ್ಗಳು ಹೇಗೆ ಇಂಟ್ರೊಡ್ಯೂಸ್ ಆಗ್ತವೆ ಅಂತೇಳಿ, ದಟ್ ಈಸ್ ವೆರಿ ಇಂಪಾರ್ಟೆಂಟ್. ಸೊ ಸಿಮಿಲರ್ಲಿ ದಿಸ್ ಡಿಫರೆನ್ಷಿಯಲ್ geometry is also a new subject. The great two things, one is to understand the Einstein theory of relativity and to understand what is the existence of this universe. So that is the thing. So very recent subject in the 18th century, this differential geometry is introduced in this classification of different branches of mathematics. Because it is, I already told you that it is very difficult to reach where we are doing the research. So that is why these slides will give you the clear information, what type of research is going on, how the research will be developed. That is why I think every mathematics students, we started with geometry, counting the numbers along with the pictures. Without picture there is no meaning, without number there is no meaning. I think you can understand. because I am the reviewer of the textbook from first standard to seventh standard. I know how we can introduce the mathematics to the our Karnataka students, especially primary school students. That is why we read all the paper, all the courses. That is my one best example, experience. That is why geometry we know. So from geometry, how we have to start with? From geometry, we have to move into the differential geometry. Differential geometry is the combination of geometry with differential calculus. Okay. Once again, I point to you that this differential calculus is also originated in the same period, that is in 18th century. I think you know, by Isaac Newton and Leibniz. You heard the names. Okay, because of them only the new concept is developed, that is differential calculus. Before that, just you mathematics thinks that so many concepts are already developed and so many mathematical models and problems are already solved. What are the methods they are using? But now everyone is using differential calculus. Without differential calculus, we never solve anything. But this is a very recent subject. But earlier, so very basic methods of solving any mathematical problem. Just imagine how they are measure a distinct objects in the universe. Just you can imagine that how they are measure the exact location of a sun, exact distance of a stars, exact the speed of the light, isn't it? So in those days that differential calculus is not there. Remember, so there are three techniques usually we are using to solve the mathematical problems, any objects in the universe. One is the best simple method is algebra, second one is geometry, and third one is analysis, particularly topology. In the latest years, topology we are using because when we can the object will take turns and rotations, then the concept will be changed. Okay. But that is differential calculus. Once that differential calculus is introduced, algebra and geometry will become weaker and weaker because this is a very big concept. From differential geometry, there are two types of differential branches are there. One is local differential geometry and global differential geometry. What we are doing research usually the global things, but we are looking into the locally. Okay, because we know that the earth is globally sphere, but we are staying this locally is a flat. I think you understand the difference globally and locally. Locally means in terms of topology, every concepts of mathematics can be developed at a point and the neighborhood of its points. This is the concept of locally. So suppose you can take that continuity, differentiability. You see that, just imagine. So continuity at a point x, right? That is the, and analytic function, it is continuously differentiable at a point and its neighborhood of its point. So like that. So that is the concept of locally and globally. But when we can look into the universe, these two concepts are very important. Locally we have to study it, but extend it to up to global things. Means all the concepts are, we have to prove either 2-dimension or 3-dimension, but we can extend it to n dimension. That's all. Okay, that is the concept of local and global. From differential geometry, along with that, some generalization of these structures is nothing but differentiable manifolds, because the universe is a different types of folds. Okay, not one fold, not one surface. We don't know that. So that is why the generalization of surfaces with differential geometry with surfaces, the study of that structure, we can call it as a differentiable manifold. But we know up to this stage we are using usually the Euclidean distance for measuring the one point to another point in the space. That is, you know. But remember how to measure the point on a space, n-dimensional space. Okay. So that is why the great mathematician Riemannian introduced the one structure, the measurement of the distance between the one point to another point. That is, we can call it as a Riemannian metric. Okay, so that is only the metric. Even till today, we have to identify the world extraordinary galaxies because of Riemannian metric. So that Riemannian metric measures the point, not point to point, vector to vector distance between. Okay, and vector field to vector field. These are all simple geometric ideas. Okay, remember, no problem. So there are so many branches of Riemannian geometry or Riemannian manifold are there. So many branches depending upon the metric structure. So we can put the Riemannian manifold to the contact structure. That is, we can call it as a contact manifold, and different structures. So many applications of Riemannian geometry. That is particularly special relativity, that general relativity, and we can move on to that cosmology. Now at present, in our India, though so many some institutes are doing research on Riemannian surface to general relativity, special relativity, and cosmology. But the continuation of that Riemannian geometry, generalization of that Riemannian geometry is our research subject, that is Finsler geometry. In the evolution of the geometry, this Finsler geometry is the last geometry till today. There is no other geometry exists. Okay, but here the difference between that Riemannian geometry and Finsler geometry is very clear. So in the Riemannian geometry, we measure the distance between the one vector to another vector. But in hello, okay, distance between one vector to another vector. But in Finsler geometry, when that Finsler is introduced with the structure, here we have to measure a vector and velocity of a vector, the moving point. It is difficult to measure, you know. So I think a vector and the line element, we call it as a line element. So this geometry is very much helpful when the particle in the universe is start to move. I think Bertrand Russell told me one thing, one very wonderful word, you can remember, complete rest is almost dead. That is why each and every person is moving one point to another point. No point is stagnant in this world, especially moving objects, isn't it? So this is, once the start moving, the structure will be changed. How to measure that type of distances? And just imagine how to measure a one point on a big ocean to the another point of a big ocean, because thousands of what we can call it as a waves are coming up, different levels of waves. So based on waves, we have to measure the distance from one point to another point. I think you recall how that waves are moving and how continuously they are moving. So then how to find the distance? So to measure such distances, it is very helpful. That is, we can call it as a Finsler geometry. From Finsler geometry, there are so many branches once again. Okay, I can leave it. This is what is that my plan of the talk. Particularly differential geometry, I will give brief introduction, general relativity and cosmology. I think you know surfaces, generalization of the surfaces is nothing but manifold, and we have to measure the distances in the manifold is nothing but metric structure. But here general relativity is different branches of general relativity is there. Particularly we are choosing our mathematical model, that is space-time, black holes, wormholes, and these are creating some curvature. That is what we can call it as a curvature. And third one is cosmology. Look at that, where we are living, how we are living, and what is our universe, what is the next to behind that universe, and when this universe is formed, when it is collapsed. These are all wonderful creations in our mind. Just imagine that, how this world is exists, how this universe is exists. Behind that, beyond that universe, anything is there? Multi-dimensional universes, or multi-universes. Are you know? Yeah, that is wonderful. Research is going on. Some textbooks, they are very well written. They are doing the entire their research. One wonderful mathematical book you should read, The Mathematical Universe. the book of that name of that book is Mathematical Universe. Entire universe can be explained in terms of mathematical models. I will tell you that how it is beautiful. I think geometry I am not going to explain, that is that is the primary concern with the shapes and size of an object, their relative position and the properties of the space. You can just concentrate color words, it is more enough. I am not going to read everything. Okay, so these colored words, not just a words, these words are the one type of courses, each one is a course. Okay, so that is why just observe that. And there are many postulates and theorems we know, because that we treated as Euclidean is the father of geometry and further things. This is the simple definition of a curve. Okay, in mathematics a curve is a object similar to a line, but that does not have to be a straight. Okay, because usually in the any interviews they are immediately ask what is curve, like that. Okay, so that is why this is the best definition, but mathematical definition is different. Mathematical definition is a curve is a differentiable function, because it takes deviation. Deviation means differentiability. Okay, it is a differentiable function, but that is defined as alpha from an interval to some manifold m is defined parametrically. Of course, there are so many representation of a curves are there, but in mathematics, in geometry, the parametric representation is only the best representation of the curve. Okay, because just to give the values of theta, the curves will be automatically created. Okay, this is sine curve and cos, I think you know. And second structure we know in mathematics, that is surface. A surface is a generalization of a plane. Okay, plane is a surface, of course, that generalization is a that is a plane, but unlike the plane it may be curved. These concepts are very important when I can enter into the relativity and cosmology. So when we can wrap, a plane can be wrapped, it is smooth, I think you know, that is smooth, then it will become a surface. And generalization of this surface, I tell you that manifold. Look at that, what is the meaning of that manifold? What we need? This is of course very difficult mathematically, but in terms of real world it is very easy, everyone will doing that. Okay, how to identify the places on a earth. So one place here is there, Tumkur, and New York City is there. In New York City one house is there. How to identify that point? Okay, how to identify the different districts in the USA? That is with the help of, I think you know, in geography we are know everything. That is a structure, but mathematically it is just a function. Look at that. To define the property continuity, in the real world object, or from that is a curve, alpha curve, or from m, by judging suitable condition not on a real world object, unknown object. Okay, not on a real world object itself, but on a chart. Remember, on a chart representative of the real world object. Chart is the new concept, I think you know. Chart, and the next concept is collection of charts, we can call it as a atlases. The structure of chart and atlas is nothing but our surface. Okay, that is, we can call it as a differentiable surface. In generally, most generalization of surface to the higher dimensional space is nothing but manifold. That is a very simple statement. But in terms of mathematics, a manifold is a topological space that locally resembles Euclidean space near each point. Means locally it is a Euclidean, but more preciously an n-dimensional manifold or n manifold is short, a topological space with a property that each point has a neighborhood that is homeomorphic to an open set of an n-dimensional Euclidean space. Means once again, by using the homeomorphic structure, we have to identify our that is surface in the entire big surface. Small surface can be identified in the big surface. That is usually we can call it as a patches. Okay, so that is another concept. Of course, topological manifold, I skipped this one. Okay, the topological structure homeomorphic, that is invertible, continuous. So the question is, look at that, why we need the manifolds, very interestingly, in terms of differential calculus. In terms of physics, in the physics, especially the applications of the physics, the physicists are never want to the discontinuity of a point. They are not allowed. Okay, discontinuity or jump of a particle or jump of a space. I think you can remember when we can launch the satellite, it escapes from one that continuity, it jumps the continuity. Just imagine that how much we have feel. Jump the continuity, it means that it is escape from our control, isn't it? Okay, that is why the physicists never allowed the discontinuity of a function. So if you can control for each and every point the continuity and differentiability, that is only the possibility to introduce this manifold structure. Okay, this is the lack behind that why the physicists are introduced this manifold is very interesting. So they never want to that what is that discontinuity or jumping, or when we can the work the particle is moving. So that is continuously differentiable. Can you understand? So that is we can call it as a CR functions or C infinity functions, or in simple word we call it as a smooth functions. Very mathematical structure, smooth functions. Look at that, a differentiable manifold is a n-dimensional M. That M stands for n-dimensional topological structure. Tau is the collection of topologies, and AR represents the CR atlas. CR atlas means the atlas is consisting of a charts, CR charts. These atlases are defined as the transition maps, means homeomorphism, diffeomorphic structures. These homeomorphic and diffeomorphic structures can glue together from our general space Rn to Rn. That transformations we can call it as a transition maps. Okay, so that is a very big concept. So that is what is that simple manifold structure, or we can call it as a smooth manifold structure. Of course, this is what I am saying, that this is pure mathematics difficult. Of course, you can see that. These are all the simple structures. What we can see that is one simple differentiable manifold is nothing but Mobius strips. Are you heard? That Mobius strips. Unchuri light off ಮಾಡ್ತೀರಿ ಇವು. Okay, that is look like tilted or twisted, but basically that surface is not twisted. Look at the ants. They are directly travel from each point to another point without taking any other steps. Okay, so similarly that one also, that is mathematically that is represented. A Mobius strip is a surface with a boundary. Mobius strip is the non-orientable surface, but it looks like a oriented. Okay, looks like a oriented, but it is non-oriented. And Mobius strip has only the one side. In other words, if you draw a path of an ant with a line on the strip, you will see that the ant passes on both sides of the surface of a strip. Okay, that is one magic. How we can look into that surface in one-dimensional surface. I think one dimension means it is a flat. Okay, next. Another interesting geometric structure, that is Klein bottle. This is also same thing. A Klein bottle was first described in 1882 by a mathematician Felix Klein. Look at that, how that surface will be formed. Klein bottle has no boundary. It has no boundary, interestingly. And Klein bottle is a non-orientable surface. Earlier one is a orientable. Okay, this is not orientable, and it is possible to obtain, to cut from it, each of which will looks like a Mobius strip. That is what is that two Mobius strips can be glued together, you can get a Klein bottle. What a beautiful surface. Just next one is, come to that metric structure is the most important to measure the distance between that one point to another point. When I give the talks on that things, somebody will ask that what is the use of that metrics and metric structures. So that is very interesting. In mathematics, metric may be referred to one or the two related, two distinct concepts. Look at that. A function that measures the distance between 2 points in a metric space. That is we know. That is metric space. Okay. Euclidean metric mod x minus y. Distance between x and y is equal to mod x minus. That is Euclidean matrix. But interestingly, in other words, in higher dimensional structure, a metric tensor in differential geometry which allows to defining length of a curve, okay, next angles and distances in the manifolds or surfaces. That is why we are using that metric. Metric tensor and metric, both are same. The tensors are different from that scalars and vectors. Especially in physics, we are using 3 types of quantities. One is, I think you know, in mathematics also we are using scalars. Second quantity is vectors, and the third physical quantity is, we can call it as a tensors. Okay, tensors are not, because that stress, force, magnetic field, I think you need to see that once we can put forcefully, it will spread in all the directions. But vector is moving along only one direction. Okay, the collection of that points can be catch into the one word, that is we can call it as a tensor. Okay, that is another third physical quantity we are using. But in terms of mathematics, these tensors are nothing but multilinear transformations. That's all. Okay, because whatever they are using in the physics, but defined in the mathematics structure only. That is interesting thing. Okay, that is why metric tensor in general relativity, a fundamental object of studying in general relativity, similar to the gravitation field in Newtonian physics. ಆಯ್ತು ಸರ್, ಟ್ರೈ ಮಾಡ್ತೀನಿ. Okay, before a hot, sir, they are serving a hot lunch, definitely I will stop my point. Okay. This is what is that Riemannian metric we are introducing. Again, we know the same metric structure, positive, definite, symmetric and bilinear. Okay. So for already time is fixed, that is why I am moving my slides. So this is what we can call it as a line element. The first line of the ds square, we can call it as a line element. That a line element can be measured the distance in all over the world. So that is very interesting. So based on that, we have to measure different types of metrics. That is Lorentzian metric, Euclidean metric, and most important, remember, we are living in the Minkowskian metric. That is very important. Riemannian space, friends, listen me, students. Where we are staying, where we are living, ಅಂದರೆ ನಾವು ಎಲ್ಲಿ ಇದೀವಿ ಅಂತ ಅಂದರೆ ಒಂದು ಆನ್ಸರ್ ಅಂತ ಹೇಳ್ಬೋದು. ರಿಮಾನಿಯನ್ ಸ್ಪೇಸಲ್ಲಿ ಮೀನ್ಕೋಸ್ಕಿಯನ್ ಮೆಟ್ರಿಕಲ್ಲಿ ನಾವು ಈಗ ಇದೀವಿ ಅಂತ ಹೇಳಿ. ಓಕೆ, ದಟ್ ಈಸ್ ದ ಐಡೆಂಟಿಫಿಕೇಶನ್ ಆಫ್ ಅವರ್ ಪಾಯಿಂಟ್ ಆನ್ ದಿ ಅರ್ತ್. ದಟ್ ಈಸ್ ಅ ವಂಡರ್ಫುಲ್ ಕಾನ್ಸೆಪ್ಟ್. ಲುಕ್ ಅಟ್ ದಟ್ Minkowski, that is I think sir is defining that eigen values. Look at that, where that eigen values are working. In everywhere we need the eigen values. Okay, so that based on that eigen values only we have to identify different types of metric. That is what is that, when delta, look at that, any metric will become a Euclidean metric. Your delta should be diagonal elements, 1 1 1 1, all are positive. But in terms of Minkowski, the first coordinate is negative, remaining is positive. That is interesting. That is we can call it as a signatures. That is metric signatures, that is depending upon the orientation of a surfaces. Of course, this is what is that very interesting application when that light cone formation in this world, how that light cone will be formatted on the surface. Different depending upon the distance between that Lorentzian elements, space like, light like and time like elements can be defined. That is the evolution of light cones is the one object. That is, you can see that, that is a wonderful concept. And this is most important, that is the space-time concept. The every general relativity and all the concept of cosmology is based on this space-time. Look at that, space-time is a 3-dimensional space with together with 1-dimensional time. Is a 4-dimensional concept. That is very interesting. But to study 4-dimensional concept in terms of mathematics is very difficult. So that is why the physicists are introduced the space-time concept along with a speed of a light. Time is not just at that is what is that point along with speed. The time can be moving along with the speed of the light. That is why the third coordinate, fourth coordinate, we are always taken as a multiplication of the time. Okay, how much that speed time will be running in this one. So this is what is that the space time is a 4-dimensional continuum. Okay, x, y, z is our 3-dimension, and ct is our 4th dimension, can be added to measure when the particle is started to moving. This is one the best example for the 4th dimensional space is Minkowski space, because we are always living in the 4th dimension. Remember, because when I am standing 3 dimension is more enough, but when start to move, we must need the time will start immediately and another direction will I need to move. Okay, so that is why that is Minkowskian space. It is very important. And how to understand? Look at that. When introducing a Minkowski space, it is important to keep the following in mind. Observers observe object. Observer, we are observer. Observe the object in the celestial world around them based on their coordinate system. We have to look into that my coordinate system. The speed of the light is same in any other coordinate system, and for the speed of the light to be the same, the axis of the coordinate system can be curved or tilted. So that can be, you can see that how we can moving that one. How that curved means that is the last one is bending, the time is also bending by when the matter will enter. Okay, so that is in the second one, that is the coordinate time. So observe different observers and look at that how the spaceship will move from point to point on a Minkowski plane, simple plane. Okay, so this is what is that how that CT will be working on different angles. Thus the last one is the space time concept. And in 1905 that Einstein proposed special theory of relativity. In 17 they give the relation between that one. And of course, this is a evolution of that, what is that, curved space-time by Albert Einstein in 1915 is proposed the first paper, that is in the general theory of relativity. That is the background. About the relativity, I think you know, that is the concept of motion, space and time. That relativity deals with these 3 concepts. Special relativity will deals with along with the speed of the light. The speed